Hi, I'm Brenna Mockler, and today I'll be talking about how we can use tidal disruption events to measure the masses of black holes. So this is particularly exciting because a lot of other measurement methods struggle at lower masses. For example, kinematic measurements, because as you decrease the mass of the black hole, the velocity near the sphere of influence will be less and it'll be harder to measure it. So here's the M-sim relation from McConnell and Ma, and it's just a lot harder to measure black hole masses in this region. However, this is actually where we find a lot more TDEs, because at higher masses, tidal disruption events will occur inside the event horizon and we won't see them. So tidal disruption events can help us fill in the black hole mass function at lower masses. But how do we actually measure the black hole mass? It turns out the luminosity of these events follows the fallback rate of debris to the black hole, and the mass fallback rate is dependent on the black hole mass. And so if we can get the fallback rate from the luminosity, then we can estimate the black hole mass from the fallback rate. And here are the scaling relations for the black hole mass with the fallback rate. We're going to focus on the time scale of the fallback rate instead of the magnitude, because there are a lot of other things that affect the magnitude of a flare than just the amount of mass. And so it's harder to constrain the black hole mass from that than it is from the time scale. So here's a plot that's going to show how the mass fallback rate depends on the black hole mass. And so we're going to increase the black hole mass. This is the disruption of a 1 solar mass star by 10 to the 5 solar mass black hole, 10 to the 6 solar mass black hole, 10 to the 7, and 10 to the 8. And so you can clearly see that the mass fallback rate lengthens with time. It's basically getting spread out over a longer period of time. However, we need to actually convert the mass fallback rate into light curves that we see, and for this, we model the events. And so the modeling takes 3 main components: the mass fallback rate from simulations, an approximation of the circularization, and then also the reprocessing, so that we go from luminosity, volumetric luminosity, to the light we actually see. For the purposes of this talk, I'm going to focus on the mass fallback rate and reprocessing. So first, the mass fallback rate. We get mass fallback rates from hydro simulations. We actually have a library of these mass fallback rates, and I'm plotting some of them here. And we have them for a variety of different impact parameters, or beta. So the impact parameter is the tidal radius over the pericenter radius. And as you decrease the pericenter radius, as you move closer to the black hole, the impact parameter increases, and as the impact parameter increases, more mass will be bound to the black hole, just because the disruption is happening closer in. And so the first thing we do is we interpolate in the impact parameter to get a single mass fallback rate. And then once we have that, we can convert it to luminosity. And then, again, we're skipping over circularization to the reprocessing. So after the debris streams collide and circularize, they form an accretion disk, and you might expect that if we're looking directly at an accretion disk, the light might be in the X-ray. However, we find that for TDEs, they are at much lower temperatures, and we explain this using an optically thick reprocessing layer. And this actually makes sense given that these events are often close to the Eddington limit, and there's going to be a lot of extra gas swirling around, so it can help reprocess, it can thermalize effectively the light. And so for this model, we simply use a black body photosphere that evolves with time depending on the mass fallback rate. So we have the radius of the black body increase as the mass fallback rate increases. Now we use a power law here. And then we just calculate the temperature. And so this is assuming, of course, that thermalization is effective at the radius of the photosphere. And this works quite well for the light curves we have, but we would like to improve upon our reprocessing with maybe some better radiative transfer calculations in the future. However, it minimizes the parameters for the simple model for now. So we put all of this into the MOSFIT transient fitting code, which is a really cool code that has a lot of different transient models. I recommend everyone check it out for fitting supernova and kilonova in addition to TDEs. It's a really nice code that I helped develop. And so we fit these light curves, and here are a couple sample fits. You can see that they seem to fit really well, which is exciting. But can we actually constrain the black hole masses? Well, it turns out we can, and I'm actually going to zoom in on the plot on the right to kind of give you a better feel for the scale, because right now the X scales aren't the same. Here, if we zoom in, now they have the same X scale, and so you can clearly see that the plot on the right has a longer lived transient than the one on the left. And this is because it's coming from a more massive black hole we were talking about earlier. So that's really cool. Finally, I'm going to compare with the actual M-sigma relation to make sure that our estimates are accurate. So we have the McConnell and Mott relation on the right, on the left, but on the right, we have the relation from Zhao et al. 2011, which actually includes measurements from AGN to get to much lower masses than you can get to with dynamical measurements. So it's better for comparing with TDEs. And we find that they seem to be quite consistent, which is really great. So I'll leave with the summary that we can estimate black hole masses with this unique method. Thank you very much.